So this lesson is about sigma notation. Sigma notation is essentially a shortcut for writing a repeated addition. So first let me start by reading out how you write or how you read this expression here. So we would say sigma or sum, that symbol is sigma, the sum as I goes from 1 to n of f of I, so let me write that down, the sum or sigma as I goes from 1 to n of f of I. And of course, what that really means is you do f of 1, that's the first number, plus f of 2, that would be the next one, plus f of 3, that would be the next one, and so on, until you finally get to f of n. Now, I has to take on positive integers, so 1, 2, 3, 4, 5, and n better be another positive integer. Now I also has a name. I is called the index. And I is not the only letter you can use. The textbook, for example, tends to use K for the index. You can use J. You can use any number you like. Typically, you will know what n is. It'll say I go from 1 to 10, and so you'll stop at 10. But you don't always know what n is, and sometimes that part of the problem is to try to find out what n is. But that's basically the general idea. Also, you don't have to start at I equals 1. You can start at I equals 0. You can start at I equals 4. You just start wherever you are, and you go up from there. So I think this is best understood with examples. Let's just do a couple of examples. All right, so let's look at these two examples here. First of all, let me read this. The first one says the sum as k goes from 1 to 6 of 2k plus 3. So what that means is I'm going to plug in k equals 1, I'm going to calculate what this is, then I'm going to plug in k equals 2, calculate what this is, plug in k equals 3, etc., all the way to k equals 6, and then add all those answers up. So this is how I write this. First I plug in k equals 1, so 2 times 1 plus 3, and then plus, and then now I plug in k equals 2. 2 times 2 plus 3, and then I plug k equals 3 in. 2 times 3 plus 3, etc. 2 times 4 plus 3, plus 2 times 5 plus 3, plus finally 2 times 6 plus 3. And I stop there because it said to stop at k equals 6. And now what I would do is I would evaluate each of these individual expressions here. So this one, 2 times 1 plus 3, turns into 5, plus this one turns into 7, plus 9, plus 11, plus 13, plus 15, and that would be my expression. Now, the question said expand each of the following. It did not say I had to evaluate or simplify. So this would be the version I'm looking for, the expanded one, where each of these has been expressed in as simple a form as I can, but I didn't actually add up that final sum. So that's how you would do that one. Let's take a look at this one. So I want to, again, read this. So this is the sum, or sigma, as I goes from 2 to 6 of I squared minus 2i. So again, I'm going to start this time at I equals 2. That's my index, I. And I'm going to plug in 2 squared minus 2 times 2. And then I'm going to do I equals 3, etc. I equals 4 until I get to I equals 6. So let's go through that one. So I start with I equals 2. 2 squared minus 2 times 2. Plus, now I plug in I equals 3. 3 squared minus 2 times 3, plus 4 squared minus 2 times 4, plus 5 squared minus 2 times 5, plus, and the last one I need to plug in because it's stop at 6. The last one is 6 squared minus 2 times 6. And then I would probably want to evaluate all of these. So 2 squared minus 2 times 2 is 0, plus 3 squared minus 2 times 3 is 9 minus 6 is 3, plus 4 squared minus 2 times 4 is 16 minus 8 is 8, plus 5 squared minus 2 times 5 is 25 minus 10 is 15, plus 6 squared minus 2 times 6, that's 36 minus 12, which is 24. And I would write my expression this way. I would not actually calculate because the question just wanted me to expand, and so I would call that done. All right, so now let's look at a couple of examples that go in a different direction. So here, what I want to do is I want to express each of the following using sigma notation. In other words, I have the actual sum and I want to summarize it into a quick sigma notation problem. So before you do anything, what you want to do is you want to figure out what the formula is for each of the individual terms. Is there a shortcut to how we got this value, this value, this value, this value, this value? And you can use any variable you like to do that. I would recommend not using n. N tends to be saved for the number at the top of the sigma notation to tell you how many terms there are. If you use it, it's okay, but I'm going to use k, for example, instead of n or I. So I'm going to use k. So I want to notice, first of all, that these numbers 1, 4, 9, 16, etc., all the way to 100, look like squares. It looks like what I was doing was I was doing k squared, and I was adding all these up. So I'm going to write sigma. I did all my k squared. So my first k value that I squared was 1. I did 1 squared, then I did 2 squared, then I did 3 squared, then I did 4 squared, etc. So I'm going to write sigma k equals 1, and then I need to figure out what the top is. The last number I squared was 10 squared to get 100. So k equals 1 to 10. So this expression, 1 plus 4 plus 9 plus 16, etc., all the way to 100, was the sum as k goes from 1 to 10 of k squared. So that is the way I would write that one in sigma notation. Now the next one's a little more complicated because coming up with this pattern is a little bit harder, but I think I can show you what it is. So first of all, notice that the numbers are 2, 5, 8, 11. I'm not going to worry about the fact that they're adding, just 2, 5, 8, 11, 14, 17, 20. I want you to notice that this is a multiple of 3 minus 1, a multiple of 3 minus 1, a multiple of 3 minus 1, etc. So this is 3 times 1 minus 1. This is 3 times 2 minus 1. This is 3 times 3 minus 1. This is 3 times 4 minus 1. 5 minus 1, 6 minus 1. So 3 times 7 minus 1 is the very last one. So I'm going to write this as 3k minus 1. Now, for the first one, I used k equals 1 because 3 times 1 is 3 minus 1 is how I got my 2. So the very first value was k equals 1. And then if I follow that out, 3 times 2 minus 1 is 5. 3 times 3 minus 1 is 8. 3 times 4 minus 1 is 11. So it looks like I keep going. And then the very last one was 3 times 7 minus 1. So the top of this sigma notation needs to be 7. So the sum, as k goes from 1 to 7, of 3k minus 1 becomes the sigma notation version of this expression. Again, the key is to forget about sigma for a second. Just focus on the individual terms of the sequence, or of the sum, technically, and figure out if you can get a formula that will get you those quickly. Typically, if you can start at k equals 1, that's great. So I noticed that this is 3 times 1 minus 1. So that would allow me to start at k equals 1. This one was 1 squared, 2 squared, 3 squared, so it allowed, again, to start at k equals 1. Okay, so there's a couple of properties of sigma notation that are going to allow us to do some calculations, some actual, like, figure out the sum in a shortcut. So the first one is that if you have two different formulas that you are adding together, and the formulas involve the index, right? So you've got an f of I and you've got a g of I, and they both involve your I, then it's okay to separate them out into two different sums and calculate this one and calculate this one. And again, this makes sense because basically you've got a formula that keeps repeating these two formulas. And if you just rearrange the terms and put all of the terms that are part of the F formula and then first, and then all the terms that are part of the G formula second, then it's okay to add them separately. Another shortcut is that if C is a constant, in other words, a number, and you're doing C times some formula, then you don't need to have C on the inside. You can factor that C out and do C times and then the sum of that function. So that's just like, C becomes the greatest common factor of all of the terms in this sum. You pull it out, and then you just do a shorter, simpler formula to calculate that one. And another one that's really useful is that if you have the sum of a constant, so you just have C plus C plus C plus C plus C, and you know there are from k equals 1 to n. In other words, there's 1, 2, 3, 4, 5, all the way to n of these. Well, then you're just adding C, 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 n times, so the answer is C times n, how many ever terms there happen to be. So these three formulas here are going to help us when we want to use a shortcut to calculate various sums. So let's do a couple of examples of that. Actually, I guess just one example of that. So we're going to use the shortcut formula. This is given to you. We will learn about the shortcut formula later in the year, but for right now, we're going to assume that this shortcut formula is true. It says that when you're adding k equals 1 to n of k, then the formula is just n plus 1 over 2. So let's say k equals 1 to n, k equals 1 to like 20 of k. That would be 20 plus 1 all over 2. So here is a sum I want to calculate. And what I could do is I could write down 17 different terms. 3 times 1 minus 4, 3 times 2 minus 4, 3 times 3 minus 4, etc. until I get to 3 times 17 minus 4 and then add them all up. But that's kind of annoying. That's a lot of work. So let's see if we can simplify this. So if I remember the formulas that I had in the previous slide, I know that when I'm adding, or in this case subtracting two formulas, 3k and minus 4, I could split that up. So I'm going to write that as sigma k equals 1 to 17 of 3k minus sigma k equals 1 to 17 of 4. Now I could also have written that as plus k equals 1 to 17 of negative 4, but I'm just going to pull the negative out. Doesn't really matter. And then I also remember that if I've got 3 times some formula, I can actually factor that 3 out. That's another one of the formulas that I gave you earlier. So equals 3 times sigma k equals 1 to 17 of k minus sigma k equals 1 to 17 of 4. Now, this expression here matches this exactly. This expression here is one of the formulas we learned in the previous slide. This 3 just sits out front. And then I'm going to apply this formula exactly because it's sigma k equals 1 to 17 of k. So it's supposed to be 17 plus 1 over 2 because n is 17 here. So I have 17 plus 1 over 2. That is the result for adding up all of those. And then minus, and now the formula for this, when you have k equals 1 to 17 of just a number, since there are 17 terms in here, it's going to be 4 times 17. So 4 times 17 is the formula from the previous slide. And now all I got to do is calculate each of these. This is 3 times 17 times 18 divided by 2 minus, and then 4 times 17. And I would need to use a calculator here. So it turns into 459 minus 68, which is going to equal 391. And that's how I can use the sum. So again, what I did here was I noticed that I am allowed to split this up because that minus sign. I can split this up because the minus sign. I can do this part of the formula and then this part of the formula separated by a minus sign. And then I'm allowed to factor out the 3, so I pulled out the 3, so I have this part of the formula, and then I have this other one from previous. And then this follows the formula that I gave you over here for finding the sum k equals 1 to n of k. It's n plus 1 over 2. And then I did that calculation, and I did this calculation from the previous slide, and then I just basically used my calculator to get the final answer. Now for your classwork assignment, this is going to be a relevant formula in addition to the 3 that I gave you on the previous slide. So you might want to write that one down if you haven't already. And that's the end of the lesson for today.